Previously, we talked about the design of reinforced concrete member subjected to the combined actions of shear and torsion. We mentioned that a member's resistance under the combined shear and torsions is typically less than its resistance when the shear and torsions are acting separately. In order to cater for this, the interactions formulas are used. As a conservative measure, ensuring that the design outcomes are always within this area where there is no chance of the members fail under the combined effect. We also mentioned the differences between the two interactions formula. One is meant for the sections with shear reinforcement, another is without the shear reinforcement. The concepts are similar, except that the fundamental principle establishing the formulas differs. In the case that these interactions formulas fail, there is no point for you to proceed with the design. The simplest way to overcome this, it would be to increase the cross-sectional area. Increasing the cross-sectional area of the member will increase the resistance in shear as well as the resistance due to the torsion. Of course, you can choose to increase the concrete strength, which can have slight influence in terms of the resistance, but I believe the implications it will not be significant. Also bear in mind that this interactions formula, particularly those with the shear reinforcement, is actually derived from the imaginary truss model within the section. We want to prevent the crushing failure of the compressive strut of concrete. Therefore, if you look at the formula, the influence of the reinforcement, there is none. This leads to our next point here. If you find that the interactions formula fail, increasing the amount of reinforcement will not help. That's why I say the simplest way for you to increase the resistance, it would be increase the sectional area. Having this understood, now let us look at the full pictures in terms of the design when the member is subjected to the shear and torsion. The one we mentioned just now. Using the interactions formula is the first step. The function of this step here, it will be like a prerequisite. You need to make sure that these sections has sufficient capacity to take the load without undergoing brittle failure. You are not supposed to skip this step and go straight with the design with the link as well as the longitudinal reinforcement, as this may lead to a risk of brittle failure of the member. That can be a concern for the survival of the structure. Therefore, your first step it will be using the interactions formula to check whether the sections has sufficient resistance in both the torsional resistance as well as the shear resistance. In the calculations, you will require the strut angle. This strut angle it will be between 22 degree to 45 degree. Both TRD max and VRD max will use the same strut angle. Assuming that the strut angles under the torsional load it will be the same as the shear load. Therefore, while calculating the resistance from the shear, you need to get the strut angle using this formula. The same strut angle will be used for the torsional load. Once this passes, only then you can proceed with the subsequent design. You will need to design for the torsional link based on the formula here and design for the shear link. This is the formula for the design of the shear link. Bear in mind that this formula for the torsional link, the area here is referring to one leg of the link. However, the calculated area for the shear link is referring to two legs. We mentioned previously the principles of the design, where the torsional reinforcement is to be added to the full bending and the shear reinforcement required. That means you will need to design the torsional link and the shear link separately. And then the final reinforcement in terms of the link, it will be the summations of the two. Make sure you do a proper conversions in terms of the area. That means this have to be multiplied by 2 before you sum them up. And then work out the size of the shear reinforcement as well as the spacing. In terms of the spacing, since you're going to use the same set of the stirrup reinforcement to cater for the torsional load and the shear load together, you will need to standardize the spacing. For effective torsional resistance, the spacing between the stirrup reinforcement cannot be more than the perimeter distance of the equivalent box section, which is this distance, as given by this formula, divided by 8. That means the spacing between the link cannot be more than the perimeter divided by 8. At the same time, there is also control in terms of the spacing for the shear reinforcement. It should not be more than 0.75 effective depth of the section. Leading you the maximum spacing, it will be the smallest value of the three. This is due to the torsional resistance. This is due to the considerations of the spacing for the shear link. How about this B? The B here refers to the smaller width of the cross section. In normal practice, we will try to avoid the spacing between the link to be greater than either side of the cross section. Therefore, you will have your spacing here to be less than all these three values as a measure to standardize the link that finally adopt to address the combined actions of shear and torsion. One more thing about the shear reinforcement, the link should look something like this. Fully anchored and closed link. This kind of link, this kind and this kind are not recommended. This type of link may be applicable for shear load, but not for the torsional resistance. Therefore, if you know that your member is designed to resist the torsional load, you will need to have your link look something like this. Now, if you see the calculation step here, especially the torsional part, it is calculated on the basis of the geometrical property of the equivalent box section. Previously, we mentioned about two possible cases for the equivalent box section. If you are designing a solid member, you will need to assume the center part here contribute very minimal to the torsional resistance. Therefore, in terms of the design, you will assume your member resisting the torsional load as per this equivalent box section. From this equivalent box section, you will need to work out the effective thickness, the effective area, the circumferences, and so on. So corrections for the equations of circumferences. This shall be the correct one. Or you can further simplify the formula into this formula. Once you're done with the design of the stirrup reinforcement, you may proceed with the design of the longitudinal reinforcement. Use this formula. The Fyk here refers to the specified yield strength of the longitudinal reinforcement. In terms of the detailing, make sure you will have at least one bar at each corner, and the maximum spacing between the longitudinal bar cannot be more than 350 mm. The longitudinal reinforcement will have to be arranged at the inner peripheral of the link. Remember that the calculated longitudinal reinforcement will need to be added to what is required for the resistance of the shear load, since we are talking about the combined actions of the shear and torsion. Now, when we talk about the combined shear and torsional load, that means we are referring to the sections here, 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 and here. When you do not actually expect any moment acting at the end support for both the continuous beam and the simply supported beam. Even so, you need to remember that there is an additional tensile force due to the shear reinforcement. Remember, in our design of the shear reinforcement, due to the imaginary thrust model, the force interactions within the strut and the reinforcement will lead to an additional force, where you need reinforcement to overcome the additional force here. This leads you to a state that when you design for the longitudinal reinforcement, whichever amount required shall be added to the amount required for the shear reinforcement in order to cater for this additional tensile force due to the shear load. To make it simple, the design of reinforced concrete member subjected to the combined actions of shear and torsion only cover three main steps. First, you check with the interactions formula. Make sure it passes so that you do not expect it fail in a brittle manner. Second step, you will design for the link. Calculate the link separately, and then the final link that you're going to propose for the sections, it will be the summations of two. There is a catch here, where the torsional link is calculated on basis of one leg, and the shear link is calculated on basis of two legs. So when you do the summations for the link, make sure you address this. Do proper conversion. And then you're going to standardize the spacing, meeting both the requirements for the torsion and the requirement for the shear, and also consider the practical applications. Now, the third step, it would be designing the longitudinal reinforcement. Although at the support, you do not have any moment, theoretically, you do not need any reinforcement at the support. However, due to the shear reinforcement, there will be additional longitudinal force due to the strut model here. You will need to provide sufficient amount of reinforcement to deal with this additional longitudinal force caused by the shear load. With that, the amount of reinforcement calculated for the torsions will need to be added for the amount of reinforcement bar required to deal with the additional tensile force due to the shear force. This is the second catch that you have to take note while designing the members under the combined shear and torsional load.